Section 16.7. Speed of sound waves. In this lesson, we will explore several key topics regarding sound waves. We will begin by examining how pressure and displacement are related within a sound wave, and how to express the relationship between their amplitudes. From there, we will walk through the derivation of the speed of sound, specifically in a gas medium. We will also compare how the speed of sound varies across different types of media, such as liquids and solids. Finally, we will look at how the speed of sound in air changes depending on the ambient temperature. A sound wave traveling through a gas can be described using two different perspectives: the displacement of the gas elements or the resulting variations in pressure. To understand the pressure change, we use the definition of the bulk modulus, represented by the capital letter B. The change in pressure is equal to the negative bulk modulus multiplied by the fractional change in volume. For a very small element of gas, with a specific cross-sectional area and a length approaching zero, this relationship can be written as the pressure change being equal to the negative bulk modulus times the partial derivative of the displacement with respect to position. If we model the displacement as a cosine function, we find that the pressure change follows a sine function, where the pressure variation is equal to the bulk modulus times the maximum displacement times the wave number, all multiplied by the sine of the quantity wave number times position minus angular frequency times time. When we compare the displacement and pressure of a sound wave, we see that they are 90 degrees out of phase with one another. This means that when the displacement of the gas molecules from their equilibrium position is zero, the pressure variation reaches its maximum value. Conversely, when the displacement is at its maximum, the pressure variation is zero. This relationship is illustrated in the graphs shown here, where the top curve represents the displacement and the bottom curve represents the pressure variation. The maximum pressure change, or pressure amplitude, is mathematically defined as the product of the bulk modulus, the maximum displacement amplitude, and the wave number. This shows that the two ways of describing a sound wave are mathematically linked through the properties of the medium. To derive the speed of sound, we consider a specific element of gas within a tube of a certain area. Imagine a piston at one end that moves at a constant speed, providing an impulse to the gas. We can analyze this using the impulse momentum theorem, which states that the change in momentum of a system is equal to the impulse applied to it. In this scenario, the impulse is calculated as the area of the tube multiplied by the change in pressure and the time interval. The diagrams on the slide illustrate the state of the gas before and after the piston moves. In the undisturbed state, the gas is in equilibrium with equal forces on both sides. Once the piston moves, a section of the gas becomes compressed, and we can track how this compression travels through the tube at the speed of sound. We can further refine our derivation by relating the pressure change to the bulk modulus. Specifically, the change in pressure is equal to the bulk modulus multiplied by the ratio of the piston speed to the speed of sound. At the same time, the change in momentum for the gas element is equal to the density of the gas times the speed of sound, the piston speed, the area, and the time interval. By setting the impulse equal to this change in momentum, we find that the density times the square of the speed of sound equals the bulk modulus. This simplifies to the final expression for the speed of sound in a gas. The speed equals the square root of the bulk modulus divided by the density of the gas. This shows that the speed is determined by both the elastic and inertial properties of the medium. The expression we just derived is actually a specific case of a very general property of mechanical waves. In general, the speed of any mechanical wave is equal to the square root of an elastic property divided by an inertial property. For a sound wave in a solid rod, the speed is the square root of Young's modulus divided by the density. For a wave on a string, it is the square root of the tension divided by the linear mass density. We can also use these relationships to rewrite our pressure-amplitude equation. Instead of using the bulk modulus, we can say the maximum pressure change is equal to the density of the medium times the speed of sound times the angular frequency times the maximum displacement. This version is often more practical because density is easier to measure than the bulk modulus. The speed of sound varies significantly depending on the medium it travels through. Looking at the table provided, we can see that sound generally travels slowest in gases, faster in liquids, and fastest in solids. For instance, in air at 0 degrees Celsius, the speed is 331 meters per second, while in hydrogen at the same temperature, it is much faster at 1,286 meters per second. In liquids like water or seawater, the speed is around 1,500 meters per second. Solids like iron and aluminum show even higher speeds, reaching over 5,000 or even 6,000 meters per second. It is important to note that these values are for longitudinal waves in bulk media. In thin rods or for transverse waves, the speeds are typically smaller. In air, the speed of sound is notably sensitive to changes in temperature. The relationship can be expressed by the formula: speed equals 331 times the square root of the quantity 1 plus the temperature in Celsius divided by 273. This formula uses 331 meters per second as the base speed at 0 degrees Celsius. If the temperature rises to 20 degrees Celsius, the speed increases to approximately 343 meters per second. We can use this for practical estimations, such as finding the distance of a lightning strike. A common rule of thumb is to count the seconds between the flash and the thunder. Dividing that time by 3 gives the distance in kilometers, while dividing by 5 gives the distance in miles. In summary, we have learned that sound waves can be described by either displacement or pressure, and these two descriptions are 90 degrees out of phase. The speed of sound in a gas is determined by the square root of the bulk modulus divided by the density, following the general rule that wave speed depends on elastic and inertial properties. We have seen that this speed increases with temperature and varies greatly between different materials. Finally, we established that the pressure amplitude is directly proportional to the density, the speed of sound, the angular frequency, and the displacement amplitude. To wrap up, let us consider a few review questions to check our understanding. First, think about why the pressure variation in a sound wave is at its maximum precisely when the displacement of the air elements is 0. This relates back to our discussion on phase differences and the physical compression of the gas. Second, if the temperature of the air were to increase from 0 degrees Celsius to 40 degrees Celsius, how would the speed of sound change? Try to use the temperature dependence formula we discussed to calculate the specific ratio of the speeds at these two different temperatures. Reflecting on these points will help solidify the relationship between the physical properties of the medium and the behavior of the sound waves passing through them.